Hi, my name is Morgan Kelly, and today I'll be talking about modeling and optimization of complex industrial systems for application to demand response. This project was co-advised by Dr. Ross Baldick and Dr. Michael Baldea at UT Austin. The main motivation for this project is this idea that our renewables vary throughout the day. So during the daytime, the light hours, you're going to have a lot of solar power influx on the grid. And in the middle of the night, you will have some wind power. Unfortunately, when we use the most electricity, it does not coincide with these high renewable times. So if we look on this first plot here, we see that renewables are peaking during the day. And our grid demand is actually peaking in the early evening hours. This is when people get home from work, when they're turning on their air conditioners, they're cooking, they're doing laundry, all these things that consume a lot of electricity. So this difference between our grid demand and the renewables availability leads to what we call a deficit. And this deficit actually directly drives electricity prices. And also to note is that when renewables aren't available and our grid demand is high, we actually have to make up this difference using fossil fuels. And so it actually leads to pretty high grid side emissions as shown in the second plot, which coincides with when these price peaks are. So we can't exactly ask people to stop using their electricity during the hottest part of the day. So turning off the air conditioner and things like that. So what we can do is look towards these industrial participants because they don't really have these human-centered demand needs. So the idea is that when electricity is cheap and grid demand is low, we can overproduce on our product in an industrial plant and then store this extra product to meet demand later. So when electricity peaks, we can turn down our production and go from here to use our previously stored product to meet demand. So how we do this is identify an optimization problem, which can generate an optimal schedule such that we minimize our electricity cost, especially during these peak hours. So the key things that a plant needs to be able to do to participate is it needs to be able to make these fast transitions. So it needs to change our electricity consumption based on the electricity price. And we also have to be able to safely store our extra product. So the idea is this optimization problem will generate this production schedule in black here, and that this dashed line will actually be the plant behavior trying to match the schedule. So to kind of demonstrate how this works, I'm going to use a cryogenic air separation unit. The process isn't that important, but it's important to note that it accounts for 2.6% of industrial electricity consumption. So it's a really high electricity consumer. And to kind of vary how much electricity it uses, we can change the feed flow rate. And that our main electricity consumption is going to come from 4 units in the process. So the idea is that if we produce gas in excess of demand, we're able to liquefy this gas and store it for later use. And so the only inlet to this is air, and our products are oxygen, nitrogen, and argon. So from here, we're actually able to just count our electricity usage as our feed into the process. And we can also calculate power consumption as well. Again, I'm not going to get too much into the details of the process in this presentation. So the idea with demand response is that the scheduling problem will feed in electricity prices, product demand, ambient conditions to the scheduling layer. The scheduling layer here is then going to send down an optimal schedule, which is U, our production set points, to the control layer for the plant. From here, these control actions are fed into the process, which then feeds this information back to the scheduling problem. So we're going to loop through this until we find a schedule which is feasible for the plant. One thing I want to draw attention to is that there's 3 different timescales. So our scheduling timescale is going to be more over hours and days. Our control horizon will be minutes to hours. And our actual process is going to respond every second or minute. So we have a lot of overlapping timescales here, which is going to make it a really stiff problem when we try to solve it. Which is unfortunate because the key goal is to solve this optimal scheduling problem in less than an hour on a standard computer. So these electricity prices, at a minimum, they're going to change every hour, but they can change as frequently as every 5 minutes. So the faster, the better in terms of solving this. There's a few approaches we can look at to doing this. We want to aim for a linear or mixed integer linear program. For one, linear programs have guaranteed optimality and generally fast solution times. Secondary to this is that current grid models are mixed integer linear programs, or MILPs. And so if we want our plant model to actually interface with the grid, this is going to be the best way to do it. The second thing I'm going to look at is utilizing the current problem structure to enable some parallel computing to try and reduce that solution time further. So I will actually model the ASU using reduced order modeling. So these models are called scale bridging models. And basically what they do is bridge the differing time scales. So our input is going to be our scheduling, set points and targets, which are going to happen every hour. And the output of the scale bridging model will actually be quality variables on the basis of every second or minute. So we can actually utilize closed loop operating data. So this will take into account the controller that I showed in the previous slide, as well as the process. So this kind of allows us to model this in a reduced order way. So the types of scale bridging models I'll use are finite step response models, which are linear, and these are, again, data-driven models, and Hammerstein-Wiener models, which are nonlinear. And so I said we needed to linearize the problem, so we're going to need to go back and make these models linear. The Hammerstein-Wiener models are mostly what I'll focus on. So this block is 3 parts. The inner block is our dynamic section. So this is actually linear. It's a state space model. And our input and output blocks are nonlinear static functions. So something like a polynomial or a piecewise linear function. Again, the input to this is the production rate from the scheduling layer, and the output will be the scheduling relevant variable W. So like a temperature or a pressure or something like that. So the first thing I'll look at is these static blocks, so these input-output nonlinearities. So the first thing I need to do is linearize these to keep the problem as an MILP. Because they're piecewise linear, I've elected to use special ordered sets of type 2, which basically states that any adjacent breakpoints here, basically an integer variable is assigned to each one, and the sum of those two has to be equal to 1. So it basically is just calculating the slope of this line and then delineating the output. So our block input will be here, and the output of it will be at the other end. So if our input is Y, then our output will chase back to this piecewise linear segment and then go to W. The benefits of these special ordered sets are that most linear optimization solvers have them built in, so their architecture is going to be a lot easier to solve, and they do result in an exact linearization, so we're not losing any information. We have a piecewise linear function, and we use special ordered sets to linearize it. We're basically just telling the program which segment of the line to use. Drawbacks would be that it introduces an integer variable for every breakpoint, and these integer variables actually lend to an exponential increase in solution time every time you add one. So we do need to be careful about how many we add. In order to look at the dynamic block, I've defined these discrete time grids. So one of the other things about solving these problems is that we need to solve them with a discrete solver. And so basically our scheduling time slots occur once every hour. So I've delineated this with index I. Within each hour, I trace over the minutes. So each of these dashed lines is a minute within the hour. This is time index J. So the idea is that we can make a scheduling step once every hour, and then we trace what the dynamics do between each hour. So these dynamic grids allow us to capture the dynamic information of the plant. So the next step is to discretize these scale bridging models. So this inner block. So I've used the I and J time grids that I previously described. Because these are differential equations, they require a state continuity constraint between scheduling time slots. So this basically says the state at the end of hour I minus 1 is equal to the state at the beginning of hour I. So your temperature at the end of hour 1 has to be equal to your temperature at the beginning of hour 2. And this is basically just to link the problem together. So if we look at the overarching problem structure, it's block angular. So this is our common problem, which would include an objective function. And basically each of the subproblems is 1 hour in our time horizon, and it's linked by this complicating continuity constraint here that says the states at the beginning of hour 2 have to be equal to the states at the end of hour 1. So you can already see that this problem size is exponentially increasing with this discretization. So basically one dynamic, just the dynamic block of the scale bridging model already has 35,000 variables contributing to the problem. This is based on 72 hours, 60 minutes within each hour, and then 8 scale bridging models to represent this plant. So this problem is quickly getting quite large. One thing I looked at was parallelizing these complicating constraints. So the idea is that if we remove these constraints, each of these problems is actually independent, these subproblems. So the idea is if you remove these complicated constraints, you can actually solve the problems independently. So you can solve them in parallel. This begs the question of what do we do about those constraints? So we do still need to account for those because they are important. So what I did was a Lagrangian relaxation. So I basically took the constraint out of the problem. I took the difference between the two sides, so the left hand and the right hand side of the constraint, and found this gamma term. And I basically penalized that on the objective. So I basically added those constraint violations to the objective, and now we're going to minimize our operating costs as well as these constraint violations. And because it's a linear problem and we know it solves to global optimality, what we know is that if there exists a solution to the problem, this Lagrangian relaxation solution will be equivalent to the optimal solution, even though we've penalized these, because if we're reaching the global optimal solution and that solution exists, then these constraint violations will be zero. So that's important to note that we're not losing any of the problem, basically veracity with this. So our optimization problem looks like this. We want to minimize our operating costs subject to timing constraints, our process models, our inventory models, initial conditions, and our process and quality constraints. And how we do this is through an iterative scheme. So first we initialize this, and these are just different parameters to calculate the penalty multiplier, gamma here. So we're solving a relaxed subproblem, which is basically the problem without the constraints in it, and they're not penalized on the objective. And then we calculate how much the constraints are basically violating, and then we penalize these and add them to the objective. And then we keep going around and solving the problem again until the constraints get to zero. And actually, because this is a linear program, it should solve on the first iteration because it is reaching global optimality. So when I did solve the problem, I got a solution time of 1.5 minutes and an optimal operating cost of just over $1,000. This is a toy plant, so the cost isn't so important as much as the cost savings. So we actually were able to save just over 1% in terms of operating costs compared to not operating under demand response. And this is pretty big given that it's these like separated air components are actually like a commoditized process. So any amount of cost you can shave off is really good. The problem size is actually just over 90,000 variables that are continuous and about 1,500 init variables. So it's not a small problem. Just to give an overview of how the solution time evolved over my PhD. So when I started, it took 97 hours to solve with this full order nonlinear model. If we solve it with the scale bridging models and we don't linearize them, it takes 5 hours. When we linearize them, it takes 11 hours. So that was a pretty big jump here. And then lastly, parallelizing it took it down to 1.5 minutes, which is significantly below our goal of solving it in an hour. So once I have this really fast problem, there's a lot of things you can do with this. So I did the demand response scheduling, which I already kind of discussed. The next thing I looked at was these grid side emissions minimization. So looking at if we prioritize minimizing emissions over minimizing costs, what happens there? I looked at uncertainty. We've looked at a few other chemical plants, as well as an industrial plant. And then I also extended this to nonlinear programs. So I'm just going to go over a few of these results I think are interesting pretty quickly. So in terms of grid side emissions reduction, what I found is that when we prioritize lowering emissions, we're actually running the risk of having a really expensive process. So in the green here, this is our minimizing emissions target. And in the summer months, it actually costs significantly more than if we don't do anything. Or if we do demand response. However, a result that I really liked was that when we seek to minimize our operating costs, we inherently do lower our emissions. So if you look at this plot, our demand response, these blue line is consistently lower than the reference. So even if we're trying to save money, we're still going to actually inherently lower our emissions. So I thought that was pretty cool. The next thing for consideration of uncertainty, I just compared a few methods of looking at uncertainty. So whether this is electricity prices or ambient conditions or product demand. And I found that if we look at like a feedback method, a moving horizon method, and chance constraints, we actually get pretty comparable solutions. And that our risk when we use this uncertainty is a lot lower than when we don't. And it really doesn't add that much computation time. It adds like 2 minutes. So I thought that was pretty cool. And this definitely would not have been possible if we didn't parallelize the program and reduce the solution time a bunch, because these uncertainty problems are quite large. And then the last thing was extending this parallel framework to nonlinear problems. The proof that we'll solve to global optimality every time is only for linear problems. So in extending this to nonlinear problems, that Lagrangian relaxation gets a little bit more complicated. So one of the things I wanted to look at was when we increase the problem size, how does the parallelized program handle it versus the not parallel program? So many of you have done parallel computing, and you're definitely going to recognize this, which is that as our number of discretization points, which is just the problem size, increases, the parallel problem right here in red actually handles much better. So it increases at a much slower rate in terms of solution time. The unparallelized program actually increases pretty exponentially as we increase the problem size. The other thing I wanted to look at was this number of subproblems. So if we increase the number of subproblems, to a certain point, our parallel solution does do better than the non-parallelized version. However, at some point, when we get to 10 intervals, so 10 subproblems, the overhead to generate these subproblems is actually too large, and then we actually do better without parallelizing. So I thought these were good parameters to know for a nonlinear problem, especially, just to see how this extends. So in conclusion, I developed a framework to do optimal scheduling of large chemical entities for participation in load shifting or demand response. In doing this, I parallelized the program, which made a significant difference in terms of solution time and problem flexibility. And then this fast solution time enabled many different directions of research, which I've looked at throughout my PhD. I'd like to thank the Baldea and Edgar research groups, as well as our funding support and all of you. It's been really great to be part of DOE CSGF. So thank you, and I'll take any questions.